Hi, my name is Matthew Legate, and for my final project, I am going to be discussing lambda calculus and its equivalence proof for Turing machines. So let's first start by talking a little bit about what lambda calculus is, and how it may or may not relate intuitively to Turing machines. So essentially, lambda calculus it's just another computation model, like Turing machines, but it's based on abstraction versus direct computation of our expressions. So in contrast to the goals of a Turing machine, in lambda calculus, we are trying to abstract away from our domain space as much as possible by using these typeless variables. And these variables, like I said, can take on any type throughout the execution of some lambda code. They are very interchangeable, and this helps keep lambda calculus highly universal by keeping it out of the domain of any specific types. Using lambda calculus, we can get a very generic model of computation without the mess of data types, confounding our knowledge of computation space. So, like I've already mentioned that it achieves some of this by using variables. In addition, you'll see kind of in this bottom image, you'll see a lambda v. So that lambda v in this fifth line is your typical lambda, I guess, expression right there. So v is now a bounded variable. V is what is being modeled by some function. And that function is being passed this application, or not application, this function E1. And this function is, again, any function in lambda calculus where it just produces some other lambda type or function or variable. And then at the bottom, we have applications as well, which is just applying a function to a function. So that covers just about the very generic background for what makes up lambda calculus. I guess an additional goal or an additional utility for lambda calculus is it provides a lot of intuition for modern programming and programming languages because of its insight into recursion properties and these like fundamental coding principles of abstraction, which has become so common across the industry. So we already know a lot about what a Turing machine is just from studies, but to bring it in context of lambda calculus, it is also a computation model. But instead of the goal of lambda calculus, which is abstracting computation models or functions or computations or problems in general, really. Instead of going down that abstraction route, it follows the kind of reverse route and takes kind of a top-down approach at specific algorithms by implementing finite states, finite transition functions, finite input alphabet, and finite tape alphabet. We do have an infinite amount of tape, but that is not important for the goals as to what a Turing machine is trying to achieve. It is a computation model, yes, but it is going in the opposite functional direction, I guess you could say, to achieve the same goal that lambda calculus does. So, in order to begin our proof of equivalence between the two lambda calculus and Turing machines, we're going to show that we can write an interpreter in each for the other. So, writing an interpreter for lambda calculus within a Turing machine is something that is given to us by the Church-Turing thesis. Given that the Turing machine is the most powerful computation model that exists, any other computation model that does exist can also be modeled within the Turing machine itself because it is at least, if not more, powerful than any other model. So thanks to the Church-Turing thesis, we can check this one off our to-do list. So to start talking about Turing machines being simulated in lambda calculus is a lot trickier because lambda calculus is very abstract by nature. So it's not even very clear what any expression is saying, let alone building one from scratch. So what we're going to do to build a Turing machine within lambda calculus is show that we can build all of its components and then do what lambda calculus does and abstract them more and more and more until we get to a full-fledged working model, a full-fledged generic working model of a Turing machine within lambda calculus. So we start off by trying to define the natural numbers, and we more or less arbitrarily define 0 to be this first lambda expression up here, where you got f, like lambda f dot lambda x dot x. So that's 0. And then to add a 1, or to increment it, all you have to do is add a self-reference incrementally in this lambda expression until you reach the desired n. And then, again, abstracting this definition, or I guess maybe formal formal definition of the natural numbers in lambda calculus, we can start to talk about mathematical functions of natural numbers, like getting a successor, which we've kind of already started talking about here, going from 1 to n. Addition, which is just a multiple successors being applied, over and over. So you just add a variable to account for the number of successor functions needed to be run, and on and on we can go on building these abstract representations of mathematical functions. So what we want to do is start to quantize the space of lambda calculus so we can start putting it in frame of a Turing machine. So Turing machines can add and subtract. They can evaluate booleans and predicates. So we need to find some kind of definition for those and then expand upon them. So we start by down here in the bottom left just saying true. Well, this is a bad I guess relative image because this is using a different combinator basis for what's representing is true, but essentially true it looks a lot like the definition for 1 and 0, or 0 and 1, but true is represented by the number 1. Anyways, we start by saying this is true, this is false, and then we build on from there. Again, we don't really have time to get into different kinds of combinators, but believe me that this just looks like a more abstract form of this, or that this is just a more abstract form of this stuff right here, which I guess you can kind of start to draw similarities to between this and expression in different bases. Anyways, so from these and, or, true, false, nots, we can start coming up with predicates for is 0 less than or equal to, and get, predecessors. It's just as important to be able to add as it is to subtract. So we need to make sure that we are able to model any kind of mathematical function, any kind of mathematical operation, really. So we're starting to cover that with abstracting Booleans and abstracting the natural numbers. And now let's continue. So simulating a Turing machine takes more than just being able to represent different, mathematical operators like plus, minus, and, or, if, then. We need some sort of structure. We need something to work with. We need to model, the tape in some way. So we're going to achieve that by creating lists in lambda calculus. But before that, we have to create pairs, which we will use for our list. So a pair is created, as can be seen in the top left here, in such a way that it's using the different properties of like if then and all that of lambda calculus to be able to take a pair or create a pair and then get the a tuple, really, and then get the first element in the tuple and the second element in the tuple with a simple call. So that is very, very important for linked lists. So in a linked list, your first element is just going to be the data in that node, and the second element is the pointer to the next node. So I didn't get to finish recording that last slide because my family busted through the door prematurely to congratulate me on graduating, which I haven't done yet, obviously, because I'm still recording this video. But anyways, I'm too tired, so I'm just going to keep powering on, and I'm just going to go to the next slide. Anyways, so we got a model for the tape with lists in whatchamacallit in frickin' lambda calculus. So now pretty much the last thing that we need to check is to make sure that we can do some sort of infinite loop to make sure that we are covering all of our bases for what a Turing machine is, because at the end of the day, a Turing machine can move around, it can read, and it can write data, and it does so by incrementally moving up and down, evaluating, or going up and down on a tape, which we're calling a list, evaluating some local thing to get your next location, evaluate the current element to get your next location. What we're going to be doing with lambda calculus is reductions for that equivalence. You reduce one portion of the expression, and that yields a new function, a new, response to go to. But anyways, so we can create a model for infinite looping with a Y Combinator, which is essentially just a self-referential self-referential function. So you just keep applying it to itself, and as you can see kind of at the bottom there, it just keeps going on forever to simulate the occurrences of yeah, of Turing machine getting stuck in an infinite loop. So we're able to. So I guess now all we need to do is whatchamacallit. I mean, we can abstract a little further if we wanted to from here. Like, if we wanted to, we could go a little bit further and actually, create a equivalence for writing. We could like create we could abstract this all the way out into a, actual full fledged representation of Turing machines within lambda calculus. But I think it's about sufficient enough to know that we have all of the components there, where it's like incrementing up and down a linked list to simulate going up and down, an infinite tape, to to get different instructions, and different reductions and yada yada yada. When you reduce a function, you are indirectly reading and writing, and you reach an acceptance state when you have reached a full reduction. So yeah, that's about I think all the building blocks. They're all the components required for a Turing machine. You can model arithmetic, and like I said, we really kind of only went in deep here with natural numbers. With adding and incrementing and decrementing, because that's what's really important for going up and down a linked list. And I guess another key feature is key differentiating factor between these two is that a linked list is infinite in only one direction, where infinite tape is infinite in both. But anyways, turns out that doesn't really matter. So yeah, um, I think that's got almost all the bases covered. I don't know. I think I might add. I may or may not add a little bit more to the end of this. I don't know. I'm so tired. If I'm being honest with you, if I get it, I'm just looking for like just C's get degrees, baby. I mean, whatever. I just want to graduate.